Fine, good afternoon. Okay, now can you remember last day we discussed about the spring networks, right? Spring networks, and that was the best place to address spring networks. Because just after gaining that knowledge, you can apply the knowledge about the spring networks. Come on, in physics. Probably this section, the knowledge or topics about the springs usually fall under mechanics, right? Under specifically under work, energy, and power. Now, okay, fine. We can do like we could have learned that thing under work, energy, and power as well. But in case like we did so, probably applications of when it comes to applications, right? Real world applications, right? So then we have to wait for probably a longer time interval, right? Until we reach this particular situation. I mean, in simple harmonic motion, to realize what kind of applications do we have when it comes to spring networks. Okay, fine. So therefore, I mean, really with you, right? That is the best place. It was the best place. For us to discuss about that thing. Can remember the technique I revealed, the particular technique I just shared with you regarding the series spin networks. Let's say, for example, we have just remind, right? Just recall what we did last day. Let's say we do have 3 springs which are connected. At the end of one, the other one, yes. Only the other one, yes. Meaning these two guys are connected in series. At the end of this one, the other one, yes. Only the other one, yes. Then again, what do you say? These two guys are in series. So these two, the springs are connected in series, and in addition to that, these two springs are also connected in series, which means all 3 are in series. Did you get that? That's the idea. But I mean, it is not wise when you say this spring is also in series with that. I mean, it is okay, right? But the point is, I mean, in case you can avoid that and stick to the couple, stick to the springs which are connected to each other, right? So that's the most, trusted way of realizing what is the exact configuration, in which these springs are connected. So it's going to be a series. It's going to be a series, right? So that's the idea, right? Fine. Now we see, for example, this one is going to have something like the 12 newtons per meter. This one is going to have, let's say, 6 newtons per meter, and let's say this one is going to have something like what? Let's say 4 newtons per meter. Just want to recall, right? Now what is it? Well, in case you have to find, this is going to be series. Series spring networks. So how we are going to recall? Series spring networks and series capacitors, condensers, another word for capacitors, right? They will work, they will behave, right? They will behave. Exactly the same way how parallel resistors are going to behave. Probably the very, very first network, right? We just discussed it. At the outset. So now when I say at the outset, that's your all of us. Probably you have gone through the networks, the connection, right? So many resistors connected to each other, probably in series, the or is in the parallel, right? And probably you got these formulas as well. The resistors are connected in series, so R1 plus R2 plus R3, right, is equal to Req. Req, equivalent resistor. In case resistors are connected in parallel, so then 1 over R1 plus 1 over R2 plus 1 over R3, right, is equal to 1 over Req. Something like that. So that is a very, very, very good point, right? For you to remember how other networks are going to work. That's the idea. We talked about that thing a lot. So no need to just emphasizing on that thing again, but wanted to make sure you can remember the point. Now, series springs, series capacitors, let's say for the time being, series springs, what? Parallel resistors. I mean, come on, same behavior. Then parallel resistors, what is it? Series springs. Other way around. So let's say series springs, parallel resistors. So now how parallel resistors are going to be? I mean, it follows 1 over R, that format, right? 1 over R, 1 over R, 1 over R is equal to 1 over R, like. So that reciprocal format. So same format is being followed by the springs, right? When they are connected in parallel resistors. So when it comes to springs, series springs. That's the idea. Okay, good. Manga, by going, very beyond that, I just, shared something, humbly, I just realized it, right? So now, in order to find out the equivalent of these three springs which are connected in series, right? What you're going to do, just I'm going to think about let's say 12, then the 6, 4, right? Just something like this. Here we do have the 112, here is 6. How many 12s should be connected in? What is it? Should be connected in. Should be connected in series. How many? How many? How many? How many? How many? 2, right? So 2 12. All these guys are going to be 12 units per meter, right? I know you know this, just to brush up. Okay, that's all fine. So 12 is just 112 the units per meter, and 6 means how many 12 guys? How many 12 guys in the series mandala? So 6 means 2. Why? Because now instead of the 6, you will connect 2 12 guys here, 1 12 and another one 12. Then they do have the spring constant. So then what is the formula? Right? Product over sum. What is that? Product over sum. POS. POS. That is a word which is usually used when it comes to information technology. The computing, right? Anyway, in case you are doing ICT, probably you have gone through that word, POS. Product over sum. But anyway, when spring constants get equal to each other, even that product over sum gets simplified to a version, right? In which we can just write one spring constant, right? Spring constant of one spring divided by number of springs. So here then we are going to replace the 6 by 2 12 guys. So then what would be the equivalent of 2 12 guys? Just 12 divided by KEQ is equal to, okay, value of one spring constant divided by number of spring constants. So 12 divided by how many guys are there? 2. 12 over 2 is going to be 6. Fine. Okay. So now here, in order to replace 4 newtons per meter, 4, how many 12 guys will be required? 12 over 3 is 4, right? So we don't need all together. How many 12 guys are there? Here 5, here 6. All together, how many 12 guys? 6. Now, what it means? Here we have 12. Instead of 6, we do have 2 12 guys. Instead of 4, we do have 3 12 guys. So altogether, how many 12 guys are connected in series? 6 12 guys. So they all are having the same spring constant, 12. So what is the KEQ? KEQ is equal 1 spring constant over number of spring constants. Number of springs or number of spring constants. Number of the value of 1 spring constant over number of springs. 12 over 6, it is going to be 2 newtons per meter. So now for me, simply this thing can be obtained. Just by using that particular way. Or else just you could have, right? You will try KQ is equal to what? 1 over 12 plus 1 over 6 plus 1 over 4. Okay. That is 1 over K give you. So then you have to get upside down, meaning what? Minus 1. K is going to be equal. Just 2 newtons per meter. Now, even though I just put this answer here, the simplification of this one is there, right? But you will take some time, you will take some time to simplify these three guys together and to reach this answer. That is what is to be prevented by using that amazing technique. That's it. Very fine. Okay. We recalled okay. Madhurami, it's time for you to start applying the applying your knowledge in applications of the spring networks, spring networks, right? And again, springs and spring networks, right? In the real world applications. Now, number one is going to be one of the systems in which we use one horizontal spring, right, with a spring constant, let's say simple K, and there will be another object. There will be another object of, let's say, mass simple M, which is attached to the end of that particular spring. And this entire system is placed on a smooth, meaning there is no friction, right? So smooth the tabletop, or maybe the, let's say, the smooth ground, or maybe on a glass top, or some kind of like, come on, the ceramic, the sheet, or maybe a bench top, whatever. But the thing is, it is supposed to be, come on, smooth, meaning there is no friction, which is going to act on moving parts of the system. Very fine. Okay. So as the spring is, come on, the spring is suspended. Actually, the word suspended is not that appropriate in this case, as the spring is lying horizontally, right? It's lying completely horizontally. This system is called, come on, first of all, the spring mass system. Basically, it's called spring mass system. Why? Because there is a spring and there is another mass which is attached to the end of the spring. So entire system is comprised by one spring and one mass, come on, which is hanging from the end of the spring. So altogether there are two objects, the spring and the mass. Hence it's called spring mass system, and everything is lying completely horizontally, right? So hence the additional word horizontal. So once you combine everything together, put into the same jargon, so it comes up to be horizontal spring mass system. Fine. Okay, so we are about to start applications of the what? The spring networks, and actually a simple harmonic motion. Fine. So leave one rule behind from the mid of the next rule with the normal colors. There are so many real world applications. There are so many real world applications, and physical systems, real world applications and physical systems, which can be proved to execute, 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 SHM, simple harmonic motion. Not the fine value, full stop. So full stop. Then continue. Right, just continue. Few systems out of the entire list few systems out of the entire list is given below. Fine. Full stop, right? That was my number one is going to be one of the let's say most simple thing. Horizontal. Horizontal spring mass system. Right. Now two is going to be vertical spring mass system. Right. Number three is going to be something really simple. Here's the word simple. Simple pendulum. And number four, let's say, two springs, mass system, and number five, let's say, a liquid column in a U-tube. Number six, an object, floating. Floating. Let's say in a liquid there are about like six, right? And so the list continues. So we can have so many other applications like the let's say two springs parallel, two springs series. But then I'm going to include them because there were few past applications from the let's say consequences of the spring systems. So therefore, just after discussing about, let's say the simple harmonic motion, which is executed by one spring mass, one spring, one mass system. So let's extend and try to analyze what will happen when you connect two springs together, maybe in parallel, maybe in series, and that particular mass of simple limb is going to be at the end of these springs. In case two springs are in series, so one spring, and then at the end the other spring, only that spring, and then mass is attached. In case springs are connected in parallel, one spring, and by the side the other spring, so there is a common support to which that particular the mass or the object of mass simple limb is attached. Those are the consequences, or we can say just extensions of the of this the main two topics. So once done, so we can extend the discussion to analyze those two systems as well. Okay, fine. List continues, but this is more than enough. The just regarding this particular level. Okay, the right fine. So leave one rule behind the from the mid of the next rule. Just I wanted you to be so clear with one particular point. What is that? Now, even though we have just listed down these systems, having said these systems are executing simple harmonic motion SHM, now onwards, from this very moment onwards, we don't know. Did you get that? We don't know. Horizontal spring mass system is going to execute. Okay. keep moving, but we don't know whether that motion is SHMOO something else. Do you get that? So what you got right now is applicable, is relevant regarding all systems listed here. Come on. And all the other systems which are not listed here but is in the list. Can you make it fine? So what it means, actually these are the basic systems. Now why I'm saying always, I mean few systems of the list, right? Because there are so many other consequences, meaning the associated systems. So they can create a system by using maybe one spring, and by using another pendulum, right? By using two masses and three springs, something like that. So in that case, you should be able to analyze that motion and show, in case they wanted you to do so, you should be able to show that new system. But actually it is going to be, it was in the list, but we did not discuss about that thing, as because they haven't specified. In case we are going to do that, so the list is going to have at least about like 50, 60 systems. At the first sight. So sometimes it is going to be really kind of like takes too much time. It's okay, fine, because you gain the knowledge, but that is not essential. That's the most important thing. That is not essential, or that is not compulsory. But because once you understand the principles lying behind these systems, these basic systems or foundation systems, right? You are supposed to be able to analyze any other system or extended associated systems with one of these systems. Did you get that? That's the idea. Fine. Fine. Okay. So that's it. In case you have that thing down, right? So we are going to start with the first one. Topic number one. Leave about like two rules behind it. Have the topic horizontal spin mass system. Horizontal spin mass system. Hey, down soon, right? Because we are working on syllabus. How many months before? Oh, it's about 8 months. That's the target. Okay. Now ready? Fine. So topic horizontal spin mass system. Okay. Back to normal colors from the mid of the next rule. So let's see. Following diagram illustrates. Following diagram illustrates. Following diagram illustrates. Following diagram illustrates a horizontal spring mass system. A horizontal spring mass system. A horizontal spring mass system, which is placed on a smooth plane, not plane, plane, smooth plane. Okay, fine. So trying to take down as soon as possible, right? So let's say we have right. This is going to be the spring. I'm going to draw this arm a little longer, right? Just to make everything, let's say, kind of the clear, right? And at the same time, the for you to be comfortable with what we are going to draw. Come on, next and next and next, right? Okay. So this is going to be natural length. So this one is going to have the spring constant simple K, and this one is going to have some mass simple M. The point is, this is going to be a smooth plane, so we don't have to bother about friction in any way. Understood? Right. So now this particular support is going to be fixed, and this is going to be smooth. plane. That plane can be a tabletop, right? A glass top, whatever, it doesn't matter, fine. So, smooth plane. Right. Let me, take this level, right? Make a reference. So now, this is going to be the natural length of this spring. You learned about them a lot, right? So now what do you mean by natural length? Genuine length, original length, undeformed length, unstretchable length, right? So which means, no tension is produced or no restoring force is acting on the spring. The spring is just, come on, standing on the tabletop, and mass is hanging or mass is attached to the end of the spring. Nothing is going to happen. Just they all are, come on, at rest. They all are still. No tensions, no extensions, no compressions. Come on, fine, completely. Just silent. Okay, fine. Now, then what you're going to do? No, same system is drawn again and again and again to show you the different. Come on, okay, status. Now let me make a copy. And in case I'm going to extend maybe up to probably somewhere like here, right? So this mass is what is it? It is lying on the, come on, plane, tabletop. But Mabada, why we have intentionally kept a gap? We talked about that thing a long time ago, just for the clarity of marking and identifying forces. Otherwise, it doesn't mean this mass is about to, come on, fly off the plane, right? Or it's just, the tabletop is about to dig in, right? While just, leaving that mass there. No, it is in contact, but why a gap? Because then we can identify whatever the forces we are about to mark 100% accurately. Okay. Once once we just draw a diagram in a way like this, actually they are in contact. Physically they are in contact, but virtually we have drawn them in a way that it seems, oh, there is a small gap. But we know, actually they are in contact. Such a diagram is also called open contact diagram. You get it? Now, so you're going to add more and more advanced words into your vocabulary of physics while learning more and more stuff, right? Now, today you got the word. What is called? Open contact diagram. Now, in case somebody will ask from you, what you have drawn here? Why that mass is, mass is flying? Or mass is just, come on, in the air. So how you can say, just by using that technical word, right? Or whatever that the scientific word, you can answer. This is the open contact diagram. That's all, right? Fine. So then, now that extension up to there from the equilibrium position or the undisturbed position, right? That position is called equilibrium position, or it's just, we can say what? Undisturbed position. Undisturbed position. Fine, here. Right? Or it's just, we can say, come on, equilibrium position. It doesn't matter. But then equilibrium, when it comes to the context of simple harmonic motion, that undisturbed word is much more, come on, the let's say appropriate. Why? Disturbing means, okay, now system is getting ready to undergo oscillations, about to undergo vibrations. Undisturbed means what? System is just hanging on, right? No disturbances, So it is not executing any vibrations or any undergoing any oscillations. That's the idea. Okay, fine. Mabutabel. Right, fine. So that's it. Then Mabuta, now I'm going to ask one small question. So then just try to answer that question, and then after that, come on. So no need to keep asking the same question regarding other systems, but because now you will come on, you will be able to answer. You will be able to understand why, because that thing was answered here, right? Now the amount by which the spring has been extended, elongated, stretched by me or by you, right? Is, let's say, capital A. Along that way, with respect to this on undisturbed level, towards right, let's say plus, towards left, let's say minus. Come on, x-axis is the origin, towards the right of the origin. What is it? Positive x coordinates towards the left of the origin. What is it? Negative x coordinates. Isn't it so? So the same thing, right? Undisturbed portion will be taken as the 0 for the measurements of the displacement. So in case you will measure something towards the right, you can have positive displacements, whereas you will measure towards left, you can have negative displacements, obvious, right? So vertical systems, what is it? Where you have declared for the displacement to be 0, with respect to that, you keep going up. It's going to be positive with respect to that undisturbed level or the equilibrium level or the level which was declared to be 0. You keep going down, definitely you are going to get some negative displacement. Simple thing, right? Fine. Madhuranomi, the point is this. I told you that I'm going to ask the question, and probably then I'm going to answer as well. So Madhurana will understand. So therefore, that question will not be repeated in upcoming cases. Why? Because I mean, in vain doing so, because you do understand what's going on, right? Now, this is just like Tati gave you 1,000 rupees in the morning just before leaving your home. You're about to go to school, then after that probably classes, then after that probably gym, not during A level, right? Fine, then let's say then we'll come back to home. So for this entire journey from the morning to the let's say evening, I mean the total amount of money Tati gave you just at the beginning of the day, beginning of the day of yours, right? Was 1,000 rupees. My simple question is, I mean, do you have any ability or any kind of let's say probability of spending more than 1,000 rupees? Given that you are having only 1,000 rupees given by Tati or maybe Ami, what is it? No, sir. I mean, in case I'm going to spend as much as I can. Maximum amount is going to be 1,000. That's all. Or it should be less than 1,000. Exactly the same way. I mean, very initial displacement, which was given by us, right? Which was given by you. Now, in this case, this mass is just like what? Come on, like let's say child, you or me, the one who is applying, or just I mean the one who gave this extension, initial extension, elongation. Come on, resembles the father, Tati, dad. So initially we gave 1,000 rupees to the child and will be released. So then child keeps on going through his or her, right? Day, going to school, then like, in the school, go to the canteen, buy some snacks, and then after that, come on, intervals, some ice creams, blah, 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 and then like with the friends, after schools, then go to classes, right? Then the what do you say? I mean, maybe expenses for the buses, I mean, lot. but everything should be within that, come on, 1,000 rupees. So simple question I'm about to ask from you is this. Don't you understand? I mean, once this mass is released, having given an extension of plus A, maximum extension which can be attained by this child, by this mass, is only plus A, never ever more than, come on, plus A. In case it is going to go to this side, it becomes minus A, right? Just come on. I mean, they two are equal. Y plus, Y minus, just because of the direction, that's all. Magnitude-wise, modulus-wise, they are equal. Right? So therefore, Malpatami, this mass will never exceed this position, ever. In case, I mean, it is going to reach or the maximum displacement which can be attained by this the mass is going to be plus A. Okay, so in case this I mean, as we have already mentioned, this plane or the tabletop is smooth, so there are no frictional forces. So mass has, come on, nothing to do against dissipative forces. There are 3 types of dissipative forces. You know what are them, right? We're going to talk about them in detail when it comes to properties of matter, the viscosity and surface tension, right? So but for the time being also you have the legal order knowledge regarding dissipative forces. Now the fine, okay. Now the other point is that in case this is smooth, so this mass has nothing to do regarding, I mean, no work has to be done regarding dissipative forces. So what? A, starting from A, okay, fine, 0 minus A, 0 plus A, 0 minus A, 0 plus A, and so forth. Like, I never mentioned it is executing simple harmonic motion. I just said it can go, come on, yeah, this way. So here, come on, displacement is 0. This way, it becomes minus. Minus wise, what would be the maximum displacement? Again, A, so minus A. Back home, home means the undisturbed position. Again, 0. Coming back home, come on, again plus A, not more than that, at least by a fraction of a millimeter. Understood the right? Now regarding the simple harmonic motion, and then the what's called this the circular motion, right? Uniform circular motion. We discussed the maximum displacement towards one side, very important, towards one side of the undisturbed position is called, what do you say? Or is defined as amplitude. Now, here's the idea letter A, capital A, right? Because of that word amplitude. So now what do you mean by amplitude? It is the maximum displacement. Number 1, maximum displacement. Number 2, that maximum displacement should be considered, towards only one side, either this side or this side, only one side. With respect to what? With respect to the undisturbed position. Why? Because that is the position at which we have declared displacement is 0, or displacement is measured with respect to that undisturbed level. To that side or to this side, maximum displacement is defined as the amplitude of the motion. Okay, they're fine. Okay, so therefore, this plus A actually stands for something called amplitude, right? Fine. Maximum. Now, let's say that's going to be diagram number 1. This is going to be diagram number 2. And I'm going to draw diagram number 3 as well. Right, that's going to be number 3. So it's just fixed, right? Now, let's say system is this way, and this mass is not the common. Okay, with respect to that level, it is somewhere here, right? Just a moment, snapshot while moving. So, in case I want to measure the displacement, it is always with respect to the common undisturbed level. So it should be this way, and let's say the displacement is going to be something like a simple E. Okay, right. Now, if I ask you to mark the forces acting on the mass, not the spring, mass. Mass is pulled, come on, by the spring, come on, towards left. So I'm going to mark the force. So it is acting on the, see, bold. You can see properly, right? So that particular, the arrowhead starts not from the spring, but from the mass. So meaning that force is acting from the mass. My question, force is acting from the mass. Can that force be the restoring force? Restoring force? What is it? Never. In case I'll ask, my Buddha, did you say never? Yeah. Why did you say so? Are you that confident? Of course, yes, sir. Never. The problem I'm going to ask, can you please just explain why? Sir, restoring force is something which is acting on the spring itself, and to accomplish the duty of taking that deformed spring back to normal. But in this case, that particular force is acting on the mass, meaning on the object, not on the spring. The spring is also acted on by that restoring force. But what we have marked here is not the restoring force, is the force which is exerted by the spring on the mass. Understood that? Right. So that understanding is a must for you to analyze complex systems like nothing. Now again, within by following 2 steps, I'm going to completely reinforce, right? Reinforce your understanding. Question number 1. That force is acting on spring or acting on the mass? Answer, acting on the mass. Restoring force is acting on what? Definitely, sir, on the spring itself. Why? Because, sir, the purpose of the restoring force is to, gain or is to bring the original configuration undisturbed, undeformed, unstretched, right? Original, genuine, natural configuration to the spring back. So therefore, definitely restoring force is acting on the spring. Oh, wow. Okay, man, I got the point. Wow. It's really good. So therefore, this is not the restoring force, never. So therefore, according to Hooke's law, if it is the restoring force, fine, restoring force is equal to minus Ke. Is this the restoring force? No, sir. Then what would be the relationship? So just F is equal Ke. Oh, why? Because that's not the restoring force. It is the external force, actually. Understood that? Now, probably you have a small question regarding this point, as because it is little complex, right? Little. So what I'm going to do is I'm going to enlarge. I'm going to draw enlarged view, right? enlarged view of the point at which this spring gets attached to the mass. Right, fine, here. So we will have the windings, and we have the okay, and we have the mass here. Now what? Mass is going to exert a force on the spring. Why? Because we just dragged it now. So therefore, this mass is going to exert a force at the end of the spring towards this way. So let's say I'm going to mark it on the spring, and that force is going to be F, right? According to Newton's third law, there will be a force by the spring on the mass along this way, which is also going to be F. Why? Because I mean there are like 5 properties to be satisfied. I mean two forces for them to become action reaction pair. I mean, do you mind if I recall? What is it? No, right? So number 1, equal in magnitude. Number 2, opposite in direction. Number 3, collinear. Number 4, acting on 2 different objects. Number 5, what is it? Homogeneous, meaning like forces. Like forces means it doesn't mean the same direction, like I mean of the same type. Gravitational, magnetic, electrostatic, normal reaction, let's say. Fine, okay. So therefore, there is something really important, and one of the very important points. Come on, I just want you to understand exactly the same way I want you to do. That's the idea. Okay, fine. So then that's it. Now what? What is that force? Wow, this force is the one. Oh, restoring force is acting on the spring. It is fine. Let me mark that thing with the red color. Wow, something like that. Right? It is acting from the spring itself, as because it is the restoring. But this force, the black one which is acting on the combo at the end of the spring, is the one which was exerted by the spring, exerted by the mass on the spring. So hence, this force is going to be what? Is the external force. Now regarding external force, I mean, how we are going to apply Hooke's law? F is equal Ke, right? I mean, we just smash them. That F is just equal to simple Ke. You know why? Because the direction of this force is along the same direction as that of the extension. Now this force is equal to this force in magnitude. So what do you say? Just write that force to be equal to modulo K. So I'm going to just write that is equal to what? Simply Ke. Okay, last point. Right. So no doubts from this point onwards while analyzing more complex systems. Sir, why minus is not there? You are the one who taught us, I mean, the F is according to Hooke's law, F is equal minus K. I am true. Minus Ke only if it is the restoring force. Right? I mean, like very important fact. Argument. Or the most powerful fact you have, or the witness you have in your hand to question from what object this particular force is acting. Acting from the mass. But restoring force is acting not on the spring, somewhere else. So how the restoring force is going to fulfill? I mean, its own duty. Not going to happen. Not going to happen. So therefore, come on. I mean, instantly, in case I mean you were, I mean, just vibrating with the same frequency with which I am also vibrating. It's not a barrier, or it's not some kind of like no obstacles, right? You don't have any obligations to understand. Wow, this force can never become restoring force. It is going to be the external force. So therefore, in case we happen to write, I mean, let's say the relationship for this force, that relationship should not have any minus sign. Why? Because that force is not the restoring force. Chapter closed. Right? Done. Now, having said so, let me mark that F value here, and I'm going to just connect this one to this point, right? That's more than enough. Enlarge the view. So now this force is going to be F. I'm going to mark that somewhere there here, right? So I say F. Can you see? Yes. Right. That's the idea. And then now regarding this position, now listen carefully. Regarding this position, if I ask Madhudami, what do you say? I mean, this object, this mass is moving towards the spring or away from the spring. Okay, let's say Madhudana raised that question or asked that question from me. I'm going to just inspect, and I'm going to say, Madhudana, I have no idea. You got it? I mean, like, what would be the answer? I mean, like, in case I'm going to answer, what would be my answer? I'm going to say, I have no idea at all. Of course, yes, right? Why? Because now, in case this mass was moving this way, fine. In that case, velocity will be this way, right? Okay, let's say once released, it keeps moving this way, and then like undisturbed position keeps moving further towards the negative side, and will come here, right? And then again keeps moving backwards, and then back to the undisturbed position. So displacement is 0. Then again, continues to reach home. I mean, like while continuing, snapshot was taken. Now what do you say? It was moving that way. So therefore, we have no idea whether it is moving this way or that way. But nobody can say exactly. Just by looking at this diagram, nobody can say, nobody can just establish or can confirm along which direction this mass is moving, towards left or towards right. No particular answer is so uncertain. So only thing is that we can say probably it's moving towards right, probably it's moving towards left. That's all. Not the guide. So therefore, I mean, we have no idea along which direction it's moving. So what I'm going to do while marking the acceleration, in case, I mean, because this mass should have some acceleration, as because it is acted on by a force. Each and every acceleration is brought onto an object by a corresponding net force. Bull cart mechanism. Cart is there. Why? Because bull is there. I mean, acceleration is the t-shirt. So net force, I am the net force. When I came to this class, I mean, the moment I was present here, t-shirt also was present, right? Meaning acceleration is also exactly at the same moment as the net force. But I have a small question to ask again. Because of the t-shirt, I came here. T-shirt took me here. Because of me, t-shirt happened to be here. T-shirt happened to follow me. To be present here. What do you say? Simple thing of the right? Because of me, t-shirt is here. Not because of the t-shirt, I am here. But when I when I appeared here, exactly at the same moment, my t-shirt did. Meaning what? Net force and the acceleration will be exactly at the same moment. Even though exactly at the same moment, what do you say? Not because of the acceleration, net force is brought. Other way around. Because of me only, come on, t-shirt is here. Because of the net force, I'm the net force. T-shirt is the acceleration. Because of me only, come on, acceleration is here. Got it, maybe? I mean, like you're wearing your t-shirt, you're wearing your blouse, you're wearing your cap, Now, come on. I mean, once the point is made clear, now just look into your surroundings and you can make so many characterize the unique examples, right? That's called understanding. Understanding, Maguda, come on. Just, I mean, the smash all these surrounding barriers, ironclad frames into small pieces so that you will get so much freedom. Come on. In a way that, I mean, you can work on your own, this area. Now tell me one more example you can take for the acceleration and the net force. Your hair and your body, meaning your hair and you. You are the net force, hair, acceleration. Nose, your nose is the acceleration. You are the net force. I mean, like how many such examples, how many such, I mean, like, more examples can be imagined. What do you say? I mean, numerous, actually, infinite numbers, actually uncountable, right? That's good understanding, mother. Good. Okay, fine. So then, here we go, and then like we got a force. Okay, fine. And now, so as because we don't know, that's the most important thing. As because we don't know along which direction this mass simple m is moving, what I'm going to do is this: I'm going to mark the acceleration of the object along the same direction. See, along the same direction, along which I mark the displacement. I just did so. In case you want, you can mark along the opposite direction as well. But I mean, marking this one, marking the acceleration along this way, has a foundation or is supported by, come on, go, a strong fact. What is that? I marked the displacement that way, right? So therefore, I marked acceleration also along the same direction. But it doesn't matter. In case acceleration is lying along the opposite direction, you will get a, come on, negative value. So that you will understand, wow, acceleration is not along the direction I have marked. Instead, it is going to be along the opposite direction or along the reverse direction. No problems. Now the fine, okay. System analysis is over. Right? Okay. So then from the mid of the next rule, assuming that you have taken down the thing, right? Including this what? Open contact diagram. What is that? Actually, they are in contact. And my brother, I just assumed, visualized. Okay, they are virtually, literally detached. Why? For the sake of identifying forces which are acting on these two, spring and the mass accurately. In contact, but was drawn by opening the contacts. It doesn't mean, contact ceases to exist physically. Physically, come on, they are in contact, right? We just do that in our visualization, mind's eye, in our imagination. So once done, such a diagram is called what? Contact was opened. Open contact diagram. Again, what is it? Was contact was closed. Closed the contact diagram. Magda, you know why I wanted to, implant or just plant tiny seeds like this in your brain, mind? Because when it comes to one of my favorite topics, electronics, right? Wait for that, right? Electronics. So I'll be using Magda, open contact diagram, right? Come on, switch is open contact, relay is open contact, relay is close contact. Wow. So you taught that, right? It seems like that word is so familiar. So open contact, meaning, of course, yes, contact is open. Close the contact. Contact is closed. That's the idea. Very much fine. Detail will be given when it comes to what? The topic called electronic devices under electronics, right? And under the subtopic called relay diagrams, which can be found usually in the syllabus. but I'll be teaching you that part. Okay, fine. So, assuming that you have taken down the diagram, or is probably screenshot, right? Fine. From the middle of the next rule, let's say in Fig 1, this is right. In Fig 1, string is in Fig 1. String is in Fig 1. String is undeformed. UNDE, same word number. String is undeformed, and therefore, no external forces and no restoring forces are acting on the spring. No external forces and no restoring forces are acting on the spring. Okay, fine, full stop. Okay, we are back to the mid of the next rule. We are about to take down just one statement regarding diagram number 2, Fig number 2, right? So let's say in Fig 2, the spring was given with a maximum extension of capital A. The spring is given with a maximum extension of capital A, and was just released. Not fine. Full stop. Right? So, same statement with the same normal colors. You are going to continue in this manner, comma. Okay, now different colors to your hand, different colors in this manner, comma, no different colors. The maximum displacement, given with respect to the undisturbed position, with respect to the undisturbed position, comma, is defined as the amplitude. Now the fine value, full stop. Okay. So now again back to normal colors, to the same statement. You continue. Therefore, amplitude is the maximum possible displacement to one side, from the undisturbed position. Maximum displacement to one side from the undisturbed position. You can write undisturbed position, undisturbed level, right? Equilibrium level, equilibrium position. It's okay, fine, highly accepted. But as I told you, while ago, undisturbed word, that particular word, undisturbed, is much more appropriate, highly qualified, right, to be used in a topic like this, or in a context like this. Why? Because they are about to get disturbed and therefore about to undergo oscillations and about to generate something called waves. Come on. We are about to, start to discuss. Right? Fine. Okay. Done. Now, regarding diagram number the 3 from the middle of the next rule. In fig 3, in fig 3, in fig 3, come on. A general position in fig 3, a general position of the mass, general position of the mass while moving, general position of the mass while moving, is shown. Fine. So now what you're going to do, you're going to just start dynamics, right? So Mamata can start from the, just leave one role, then after that can start under one small topic called dynamics, right? So if I apply, let's say, equation, just the equation, let's say, to the spring, or let's say by Hooke's law, right? I'm going to just write Hooke's law, right? So now F is equal simply KE. Why? Because we are not talking about this red force, I'm talking about this black force. So therefore what? That is going to be the external force. So along the same direction as that of the extension, or probably the compression, what do you say? They both are along the same direction. So therefore, there is no necessity or minus sign is not required. We discuss about that thing a lot. Fine. So therefore, F is equal K. Done. Now the having that thing there, I'm going to apply, let's say, for the mass. Yes, I'm going to say mass. You also can take down some, right? I'm going to apply along that way, F is equal MA. Or probably we can apply along the, let's say that way, but because force is acting along that way, right? So I'm going to say F is equal MA along that way. You are completely free. You have the entire, freedom. You can apply along this way or that way, but be consistent. You will get what I'm going to get this area. Okay, fine. In case you want, just come on, experiment on that and try to realize it doesn't matter the way of applying the equation until I am consistent. I'm going to get exactly the same answer, exactly the same expression, exactly the same relationship as he got. This area. Okay, good. Now the fine. So then I'm going to apply F is equal in the equation. So only force acting is going to be just the here see F. So let me write that therefore F is equal to mass simple M, and I have a small problem regarding the acceleration. Why? Acceleration is marked along that way, but equation is applied along this way. So it should be plus A or minus A. What is it? That's the idea. Minus simple A is there. Now I can say but F is equal K into simple E. So this F can be replaced by KE. Therefore, KE is equal to minus MA, and let me make that simple A B subject minus K over simple M in the reverse, and E is there. This mimics or that guy, kind of like the shows exactly the same form as that of what? The standard equation for the simple harmonic motion. Simple A is equal minus omega squared y. So this takes the same form as that. Simple A is equal minus omega squared y. You get that? Just like you got one equation. How does it? You got one equation y is equal to 2 times x plus 4, right? In case you are doing maths, it's nothing for you, right? I mean, for the math students. So one more, maybe like just to sharpen up your edges, one more bit of advice I can give you. Y is equal mx plus c was probably the only way you knew to write the equation of a straight line till advanced level, till the end of your O-levels. But there are more than, 3 ways of writing on the unique equation for a straight line. There are more than about, 3 ways of writing the equations. Now y is equal to mx plus c is just the most simplest way. So there are more forms, which represent or which stand the for a straight line. Now the question is this: now in case you find, let's say you got something like this, and you are going to compare. Why, my goodness, that particular equation takes the form y is equal to mx plus c, and you're going to tell me, sir, it's okay, fine. What I got is representing a straight line with the gradient 2 and with the y-intercept. Very important, don't just say intercept, right? Now you are grown. Actually, you are a grown up, right? So therefore, intercept, there are 2 intercepts. We do have y-intercept, we do have x-intercept. So now, what is this? Plus 7 is not the x-intercept, it is the y-intercept. So you have to be careful, you have to be that keen and that accurate. Okay, it's not just for let's say some 65 or probably 80, right? Or probably 85 or probably 70, 75, not for A, but for ranks. Rankers should know them properly. Probably not the normal. Normal means students who are going to take just A. Probably it is not that important. But for a ranker, just let me tell you, everything is important. Now I ask you to Mabudami, they say, boron, aluminium, gallium, indium, thallium, carbon, silicon, germanium, tin, lead, nitrogen, phosphorus, arsenic, cadmium, bismuth. Now these things, helium, neon, argon, krypton, xenon, radon, all these stuff. So do I have to study, or I'm supposed to remember? Those questions are not relevant when it comes to rankers, right? If you ask a question, so do I supposed to, or just am I supposed to? Do I need to? So definitely, I'm going to say, yes, of course. But given that you have a dream, which will definitely come true to touch one of these ranks, right? Say, good, okay. So now I just explained. Now this takes what you obtained, takes the standard form of the simple harmonic equation. Simple A is equal minus omega squared y. So, what you got actually resembles the standard form of the SHM, which concludes, wow, my system is executing what motion? Simple harmonic motion. Now only we got to know, wow, that horizontal spring mass system, which is on a smooth tabletop, is executing what? SHM. Till this particular point, or till this moment, what we could have said, that mass and the spring, especially the mass, keeps oscillating. Is it SHM? I don't know. It keeps just oscillating, vibrating. That's all we would have said in case somebody questioned before reaching this point. But after reaching, now we can definitely say or we can confirm system is executing simple harmonic motion. Now, got it? Fine. Okay. Assume that you are here. Assuming that you are, you are here, right? So we are going to write one statement with different colors. Therefore, the equation which explains the equation which explains the motion of the horizontal spring mass system, resembles. Sir, how to write? Resembles the standard equation of the SHM, simple A is equal minus omega squared y, resembles the standard equation of the SHM, simple A is equal minus omega squared y. Full stop. Therefore, horizontal spring mass system executes simple harmonic motion. SHM, right? So executes simple harmonic motion. Fine, good. Now having that thing said, so what I'm going to do is just I'm going to erase this diagram, right? No worries. Just remember all screenshots are available on demand. A new system is a new system for you, especially for you, as because you are the big seniors right now, just after 21. So meaning 21 batch, right? So a new system is getting ready for you. Actually, about like 85% is almost installed. So after that, what's going to happen? All these screenshots and the recordings and everything will be available in the server. So just after, let's say you just want to watch that, right? So then the most probably through the email, or probably maybe commonly in a way that all can watch that video, right, one more time. So will be available. For the time being, it is not that easy, but because the probably just after your class, sometimes going to start another class, right? So likewise, things keep going. Or is some engineering stuff, right? So that's the idea. But anyway, now very soon that thing will be available, and you will be noticed, acknowledged in advance. Now, fine. Now, when I'm going to compare these two guys, right? So I'm going to say by comparison. See here, A, instead of acceleration, A is there. Instead of omega squared, what? This block is there. Instead of minus is there. Instead of y, the displacement. Okay, fine. Extension is also a displacement. No, fine. So now, so you also can take down, right? I'm going to say by comparison, come on. Omega squared is equal to k divided by simple m. So therefore, what would be the value for the omega? K over simple m whole square root. But time period capability is equal to 2 pi over omega. Something we discussed, simple relationship we discussed in uniform circular motion and rotational dynamics, right? So that value can be inserted here, but this guy is in the denominator. What's going to happen? M will come to the numerator while leaving simple k in the denominator. So therefore, capability is going to be equal to what? 2 times pi, whole thing square root. Simple m is going to be up, k will be down. That relationship, what do you say? You have to remember. Sir, they are not going to do this. I mean, you give this relationship in the paper? That depends, my brother. Now, there are past papers, when it comes to paper 2, part A, structured says. Sometimes they have given this relationship, right? And they keep asking associated questions, structured questions. But when it comes to the most important paper, and the paper, actually, let's say, entertaining paper, fun paper, what? MCQ. Why? Because no worries, you can just mark one answer, whether it is right or wrong, right? At the same time, in case you will get the responsibility to make yourself prepared to mark the correct answer in the exams. You know what? I mean, no talks, no nothing, no contributions, no weights. Weight means the percentage of contribution. It's just the 100%. You marked one MCQ, 1 mark. 74. You marked one more, correct? It becomes 75. That's the area. So fun paper, but the most common. I mean, like important, and at the same time, the what do you say, affecting paper, right? Okay. Now, fine. So then you got the equation. Let me write one more time. T is equal to pi. Volume square root simple m over k is there. I'm going to just okay. So that thing. Okay, fine. Right. Now we can just erase that part just after having a screenshot. Now we know the time period, no? Neither. We know the time period by using simple M means what? The mass of that hanging mass, and simple K. Spring constant, force constant, right? The stiffness constant of the spring. You know all about that. So time period is decided only by the mass of the object attached and the spring constant of the spring. Do we have anything in the equation which depends on the gravity or a local parameter? Sir, did you say local parameter? Yeah. A parameter or a physical quantity which changes from place to place, right? From planet to planet. Now you have the system, horizontal spring mass system, and you have that system, or the, let's say, on the surface of the Earth. And after some time interval, probably you're going to take that to the surface of the Mars, or maybe to the space. What do you say? Mass changes? No. Spring constant changes? No. Meaning what? Time period of the system. Of the system. Time period of the system, and hence the frequency also. What do you say? Is completely unaffected, whether it is on the Earth, or it is on the Mars, or it is on the Moon, or somewhere in the interstellar. Meaning the outer space. We say just interstellar space. Interstellar space, right? Or just we can say outer space. The simple word, outer space. Now, fine. So then okay. So now let me just write frequency. So I'm going to say just frequency. So comma simple f or simple f comma frequency f is equal to 1 over time period capital T. So therefore, let me take the reciprocal of that entire relationship, which makes 1 over 2 pi whole thing square root. K goes up, simple it comes down. Okay, so one more time, simple f is equal to 1 over 2 times pi whole thing square root, simple K over simple n is there. That is the relationship for the frequency. Now, again, regarding frequency, in case you will get frequency first, you can decide, simple K, simple M. They are not the local variables, meaning they are not going to undergo changes depending on the place where they are, right? I mean, they remain constant, whether it is on the Earth's surface or somewhere they are on the surface of the moon, or surface on the Mars, right? I mean, those parameters never change. I mean, what? So frequency, time period, I mean, of this horizontal instrument system remains constant throughout the entire universe. Let's say, yeah, very fine. Okay. So once done, assuming that you are here, right? So somewhere there here, different colors, put a star, asterisk, right? And take down like this. Time period, time period, time period, and the frequency of the system, time period, and the frequency of the system, time period, and the frequency of the system, depend only on the mass of the object and the spring constant of the spring only, or depends only on the mass of the object and the spring constant of the spring. Full stop. They never change. They never change depending on whether the system is on the Earth or on the moon or in the outer space, or in the outer space. Outer space. Mark down. Now when you write, when you finish writing outer space, then you should have a semicolon. Hence, time period, as well as frequency, time period, as well as frequency of the horizontal spring mass system, horizontal spring mass system remains constant, remains constant. Over the fine? Okay. Very fine. Okay. So it's something like this. Now, when it comes to mass, which is some is suspended or just attached to the end of the spring. So something like this. Just assume this spring is placed, right? And the whatever the mass is placed on the horizontal or the tabletop. This can be K, and this mass is going to be simple M. How about this, right? Smooth plane. The mass of the spring, what do you say, is always zero. I mean, theoretically fine. Theoretically it's okay. Theoretically we do have real gases. Theoretically we do have, ideal or perfect gases. Practically we do have real gases. Practically we don't have, ideal gases. All right. So I mean, theoretically we do have smooth planes. Practically we don't have smooth planes. Theoretically we do have point objects. Practically we don't have point objects. Got it? So the things are always like this in physics. Sometimes we just exaggerate the situation, right? Exaggerate the situation to make the things simple. Why? Because if it is simple, we can study that thing in detail, and we can probably predict some important stuff but they are not probably 100%, 100% parallel with the nature, but at least about like 99% is okay. Then what? That is accurate enough for us to come on, continue with this area. Okay. Fine. Then this particular spring, is not okay. Fine. We say the just is a very lightweight, just like massless spring, right? But actually, what do you say? And when it comes to normal, reality, what? In theory, we had done so many approximations. We said the mass of the spring is zero or lightweight. So therefore, we're going to take the mass of the spring to be zero, right? Approximating. But in reality, what do you say? That spring definitely is going to have some mass, right? And my Buddha, that particular mass. Okay, so the mass of the spring, if it is something like, let's say, the capital M, or let's say M dash, just avoid, right? Any confusion? Let's say M dash. So M dash is equal to the total mass of the spring, right? But remember, what is important, Martha, is not the total mass, but something called effective mass of the spring. Now, let me give you, just an example. Martha, let's say you have a bicycle, right? Now, this example is why, just for you to understand what is meant by effective mass of the spring. Now, S stands for the spring. Effective mass of the spring, MS. Now, what do you mean by effective mass? Okay, fine. Is to be understood by this. With the help of this example, right? Now you have a bike. Okay, that's fine. Here we have the handle, and then like I say, here we have the frame. Fine. Here we have the that part there. We have this one, and it comes somewhere there here. So we have the pedal, right? Okay, fine. All that. And here we have that the wheel and the shoe, right? Fine. Sprockets are there. Those is all. Come on, sprocket wheels or gear wheels. Big one is here. Small one is there. And at the same time, a luggage is there. You got it? Now, in case you want to have a ride, you want to just use the bike to, let's say, go to school. I just want to ask one small question. Maguda, is it compulsory for you to have this luggage? Without having the luggage, can't you ride the bike and come on, go to school? Of course, yes. So probably I'm going to, I'm going to put that whatever that okay, fine, backpack will be there, and then come on. So I keep riding. Probably that is just come on, standing there, but actually I don't want that. It is there, but I don't want that. So M dash includes some more mass, which is not required, right? Meaning this system can, this mass can be given with the same amplitude, right? Same amplitude. So can undergo same simple harmonic motion with the effective mass of this spring, which is definitely lesser than, right? Little lesser than the total mass of the spring. It's just like the luggage of your bicycle. Probably you don't want that part. You just, let's say you're going to remove that, right? So yet you can ride the bike, no problem. But now that luggage appears somewhere here as a different, let's say, the different the part. Correct? Now you're gonna remove that. So what is effective is that. Understood? So there are full spring, full spring means come on with the luggage also. But actually we are not going to use that luggage, which means the actually taking that luggage come on into account is not relevant. Why? Because when it comes to the effective minimum, what is the most required, most essential is only the bicycle. We don't want that part. But somehow we can manage. You have the backpack, so you have books and everything there, water bottle and everything. You can just keep riding. Therefore, so the mass, of the spring, which can, which can just execute or which can produce the same identical simple harmonic motion with the least number of windings is called effective mass of the spring. Did you get that? Effective mass. So removed, that luggage was removed. So what I'm going to get is only the two wheels, the frame, chain, and then handle and the seat, most essential parts only. So effectively, that is the bicycle. So I'm going to ride to get what I want done. To get what I want done. I don't want the total number of windings. Some of them are there just because they were. Right? I can produce the same simple harmonic motion instead, by using minimum number of windings. Right? So if you take that minimum number of windings, for example, just assume you got the spring with that minimum number of windings, then what would be the mass of that spring with the minimum number of windings? That mass is called effective mass of the spring. You got it, fine. Effective mass of the spring. My brother, I am probably humbly more than 100% sure you understood like nothing. But in case yet, errors can creep, right? So in case you have something, so I just wanted to get that thing clarified. Chat is there. Or if you can ask for, you can raise your hands. You can ask for what? Sir, can you just grant the permissions to unmute the whatever that microphone? Or yes, you can say, sir, I want to talk to you. Or I want to just say something. I'm going to just leave that thing. What is it? The unmuted, so that you can talk to me, no problem, right? In case you have something like that, please, feel my so free. Just I have muted that thing, not because I really want, right? Or I wanted, simply because of the fact that to avoid any count. In your surroundings there can be so many background noises, right? Probably you have sisters, brothers, probably elder brothers, the elder sisters, ammi is there, tati is there. They should have their freedom, even though you are studying while I'm teaching, right? So probably they talk. Come on, it should happen. But when it comes to this situation, it is going to be what? Kind of yeah. So so therefore that's why it is kept muted, right? So just in case you want, just give me a hint. I'm going to unmute that thing completely, right? You can talk to me, no problem. Fine, done. So Mabuda, what do you mean by effective mass? Effective mass of the spring. So the mass of the spring with the minimum number of windings, which is or with which the spring is capable of producing what? Exactly the same effect as was produced by the full spring. Experiments show that usually, when you take these two guys into account, right? This ms, effective mass, is about 1/3 of the total mass of the spring. These things are little, come on, away from the scope of the syllabus. Now, in the single medium class, when I was teaching what's called this the diffraction and scattering, in Sinhala we say vivartanaya saha prakiranaya. I was explaining why daytime, come on, sky is bluish. Why when it comes to dusk, somewhere around maybe 5:30, 6:30, why it is yellowish, let's say brown? Completely to be explained by using what? Something called not diffraction, but scattering. Which is a theory which is enhanced or developed by James Clerk Maxwell under a very let's say complex but yet very important theory called Maxwell's electromagnetic theory. So we extracted some facts from the electromagnetic theory of Maxwell's, and we explained the amount of scattering is proportional to what? Frequency to the power of 4 is proportional to what? 1 over lambda to the power of 4. Lambda to the power of 4. Right? So, which is going to make you kind of like, which will place you, in the next, probably level, right? So while writing your answers, in case you are going to grab one of these points and you're gonna put them within your answer, you are spicing your answer in a way that, come on, examiners are getting amazed. So while making, come on, a big impression. You know what? Always what I'm telling you, to what extent you can impress your examiners, it is that easy for you to earn marks. That's it. Good. Okay. I'm going to leave this bicycle thing also, right? So then you can understand the what is that? Same thing can be same result can be obtained even without having the luggage. Okay. Then what I effectively need or what I effectively want is just the bicycle. But it doesn't matter when it comes to in everyday life. When Tati bought that bicycle, it already had that luggage. It doesn't matter. Not fine, but it's not the effective thing. Okay, fine, good. Right, done. So we're gonna take on that part. Assuming that you are here, somewhere there, right? So with the normal colors. So let's say, even though the spring in the above system, even though the spring in the above system was assumed to have almost zero mass, in reality, the spring should have some mass. Spring should have some mass. This is how we are going to write it, right? Should have some mass, say simple m dash. That's how in English we write some mass, say m dash. Okay, there, right? M dash. Full stop. M dash is. the mass of the full spring, M dash is the mass of the full spring, is the mass of the full spring, even though spring could, even though the spring could produce the same effect with lesser number of windings, lesser, lesser number of windings. Now fine value, full stop. Okay, now different colors to your hand. Same paragraph. Okay, same statement. Continue. The mass of a spring, with WITH, with a minimum number of windings, minimum number of windings, while producing WHILE, while producing the same effect, Makatakuma is called effective mass. Maka within brackets MS. Effective mass within brackets MS. Close brackets of the spring. Effective mass of the spring. Maka fine. Full stop. Okay. From the mid of the next rule. Again, different colors. Experiments show that the effective mass for a given spring, is about, not exactly, is about 1/3 of its full mass, M dash. Is about 1/3 of its full mass, M dash. Now, okay, there. Right. Now, you know what? Let me get this one right. And now, you know me, even though we have the full bicycle there, bicycle with the luggage, actually, we don't want that luggage, right? We just have a ride. So therefore, what I'm going to do is, even though M dash is the one which was provided at the beginning or at the outset, I'm going to just consider MS. Why? Because just with MS, I can get the things done. Right? Fine. Now what? Time period capability is equal to pi, whole thing square root simple M over simple K, assuming that what? Only that guy is going to have a mass. His spring's mass is going to be 0. Right? But in reality, that spring is also going to have some effective mass called MS. So what would be the total mass then? Obviously, come on, that MS, that MS can be added to K. Then it's just like apple plus pineapple now. Apple plus pineapple is going to be fruit salad now, not the apple or pineapple now. That's the idea. Cannot be added. Why? Because they are heterogeneous. They actually unlike. That's the idea. Unlike the features. For me, it should be the total mass. Total mass means the mass of the object plus effective mass of the spring. So therefore, when effective mass is taken into count of the comma. Time period capital T is equal 2 times pi whole thing square root simple m plus ms divided by spring constant is that. Okay, the right. Maltami, that total mass of the spring was m dash neither. It was just m dash in it. Total mass, or we say like full mass. Full mass was m dash now. So in case they had given that thing in terms of full mass of the, the mass of the spring as the full mass, remember, it is not the full mass which comes here. Come on, 1/3 of the full mass, which is the effective mass. So we can say, but M effective or MS is 1/3 of the full mass M dash. So I can just write the time period. Capital T is equal to 2 times pi whole thing square root. Simple M plus M dash divided by 3, or just we can say 1/3 M dash over simple K is that, right? One more time. Capital T is equal 2 times pi simple M plus M effective over K whole thing square root. At the same time, is equal to pi whole thing square root. Simple M plus then the 1/3 of the full mass over simple K is that. Right. Anyway, these are the things you should know, right? Now, in case you won't feel, so comfortable, during the exam or while answering the paper, right? Just come on, as you feel right now.